Good day guys, welcome back to our YouTube channel. So as always, I'm Stiffler and Stiffler is me. So we are back on work, energy and power. So I started on mechanical energy so that you can understand mechanical energy before we can go to work, energy and power. Mechanical energy is a grade 10 topic. So if you haven't watched it, guys, click on this link that is provided there so that you can be able to watch mechanical energy. So today we're talking about work, energy and power, right? So I really advise you guys, if you have missed these topics, please revisit these topics so that you can be able to do work, energy and power, because work, energy and power is a super topic that that touches many parts, right? So if you don't understand the vectors, I advise you to go and study the vectors, or you can watch the vectors on our YouTube channel. And if you don't understand the forces as well, you can as well watch on our YouTube channel. And mechanical energy, as I said, I did the mechanical energy just a few days back. So now we are about to talk about work, energy and power. Work, energy and power, right? So work can be described in many ways, right? But when you are talking about physics, or when you're talking about this topic, how do we describe work? So work can be explained like this in physics, right? So if a constant force, F acts on an object, if a constant force F acts on an object, right, and it moves or displaces a displacement then work is done. So if a constant force F acts on an object and it moves, so if that object moves, so this is just an example, like if you're having something like this, right? So this object here being applied by a force like this, a constant force. So this force is applying on this object. So if this force can cause this object to move from point A to point B, so this is point A and this is point B. So if that happens and we are having something like this, so this is our changing X. So if this object can move from this side to come at another point, so this object shifted to come there, so this is a displacement. So if this constant force acts on this object and this object is able to come there, then there is work done. So there is work done. So work is done by a constant force F acting on an object and it moves, a displacement changing X. Then that is work done. So what happens when work is done? What happens when work is done? So when work is done, as I explained, that this object moved from this point to get to this point, this is our displacement. So when work is done, it means that our object moves from point A to point B. But now when work is done, now energy is transferred. Energy is transferred. So that is the direct relationship between work done and energy. When work is done, energy is transferred, right? When work is done, energy is transferred. So now we're going to talk about some other things that affects the energy transfer, because energy can be transferred to the object. So energy can be transferred to the object, and when energy is transferred to the object, this is called a positive work done. This is called a positive work done. So it means that energy to the object, energy is gained. So energy is gained by the what? By the object. When a positive work is done, it means that this object has gained energy, right? Energy is gained by the object when positive work is done, when energy is transferred to the object. So this is when positive work is done. So this is positive, right? Positive work is done. So now let's see what happens when the opposite happens, right? So sometimes energy can be transferred from the object now. Energy can be transferred from the object. So again, it can be transferred from the object. And when this happens, we say this is negative work done. This is negative work. So this is negative work. When negative work is done, it means that energy is transferred away from the object, right? So that is negative work. And what happens with the loss? So it means that energy is lost by the what? By the object. So energy is lost by the what? By the object. This is what happens between positive work and negative work. Don't worry about that now. I'll explain that in few moments, right? But now I just want to explain the difference between work and energy. So when work is done, energy is transferred, right? So when work is done, energy is transferred. Remember we said in the grade 10 topic that energy cannot be created or destroyed, but it can be transformed from one form to the other, or it can be transferred from one object to the other, right? So let's just write that in writing. Let's put that in writing. So when energy cannot be created or destroyed, it can be transferred from one object to the other, right? So it means that here what is happening, it means that the person that is applying this force, or anything that is applying this force, is transferring energy to the object, right? So energy is being transferred from this person to the object, right? So that is the transfer of energy. And if there's a force that is opposing this, it means that energy is lost by the object and it moves to what? To whatever that is causing this to lose energy. That is how energy works. Energy cannot be created or destroyed. It can be transformed from one form to the other, right? So now let's continue and see the grade 12 content, what really happens. So now, since I described that work, when a constant force acts on an object, it will cause the object to move. It will cause the object to move a displacement like this. And if it causes a displacement like that, then work is done. So how can we put that in a definition? So in grade 12, we know that work is the product. Work is the product of a constant force acting on an object and the displacement that it moves. That is work. Work is the product of a constant force acting on an object and the displacement that it moves. So it means that mathematically we can write it like that. So it means that work done by any force, right? Work done by the force is equals to that force, the constant force, change in displacement, and we also write cos of theta, right? We also write cos of theta. So it is force multiplied by the displacement multiplied by the cos of theta, right? So now I want to explain what does this mean, so that it won't trouble you and it won't give you a problem. So sometimes you can write this formula like it's equals to force and then changing x, and you don't have to worry about the cos theta. After I explain what happens with this cos theta, then you won't have to worry about this theta anymore, right? So let's go on. So now let's talk about the angle theta and work done. What actually happens between the angle theta and the work done, right? I want you to understand this so that you won't have a problem with this anymore, right? So just take a look at this. If this object is traveling on a straight horizontal path going to the right, and there's a force that is applied like this, right? So this is our force. So we're having, let's say actually we're having this force. So if you can check the angle between where this is going and the force, it is 0, because you can also represent this force like this. So it means that the angle between the force and this path is 0. So it means that our theta is equals to 0 there, right? And again, if we have another force, just bear with me, guys. So if we have another force that is acting like this, and we have a theta there, right? So if we're having a theta, this force is going, it is applied at an angle of theta, but this object is going that way. If you can see there, if you can check, theta is less than 90 degrees, right? So whenever we are having a situation like this, when theta is less than 90 degrees, when theta is less than 90 degrees, so this is our 90 degrees, guys. So if your theta is less than 90 degrees, what happens is that if you place, again we said our formula is work is equals to force and then multiply by change in x cos of theta, right? So if our theta is less than 90 degrees, we are always going to get a positive value there. So our ratio will always be positive. So what happens now is that this will show that we are having a positive work done. So we're going to have a positive work done because of theta being positive, or theta being less than 90 degrees, right? So whenever we're having theta less than 90 degrees, we are going to have a positive work done. And positive work done, I said, energy is transferred to the object, or energy is gained by the object. So if our theta is less than 90 degrees, whatever the situation is, it means that we're going to have a positive work done, energy is transferred to the object, and also energy is gained by the object, right? So that is the scenario when we are having a positive work done. We're going to have a positive work done, right? So let's take a look at an example that is talking about positive work done, right? Okay, as we are still on positive work done, I want to explain something so that it will be so much easy for you to work with these forces. Suppose we're having this object that is going in this direction again to the right, and we're having your object that is being pulled by the force F acting at an angle of maybe, let's say, 60 degrees, right? So this 60 degrees, this force is, let's say, 50 newtons. This is what is happening like that. And it means that this displacement that this object moved, it is 10 meters. It moved 10 meters between these 2 points, between point A and point B, right? And they say, what is the work done? And is it a positive work or is it a negative work? So the simplest clue that I want you to do that will help you to solve any work, energy, and power questions, right? So let's take a look at this force. This force is acting at an angle of 60, right? According to the formula that they gave us, it is work is equals to force and then cos of theta. So this theta, it will mean that theta is this angle that is there, right? It is the angle between the force applied and the horizontal plane, which is 60 degrees. So it will mean that our work is equals to the force, which is 50, the displacement, which is 10, and then cos of 60 degrees. And you can punch that in the calculator and you're going to get 250 joules. That is positive. So it means that this object gained 250 joules. So it means that the energy that is transferred to the object, it is 250 joules transferred. So 250 joules is transferred to the object. The object gained 250 joules because of this force that acted on the object. But how do I want you to be able to calculate these, guys? I want you to forget about this, because this most of the times it makes it can make life complicated if you don't understand what is really going on, right? So if you want to understand what is really going on, let's make this force and put it in its component, the horizontal component. So if you can put any force in its horizontal component, they'll be easier to work with without using this cos theta. How do I mean this, guys? I mean this. If you take a look at F, this force is having a vertical component and it is also having a horizontal component, which most of the time we call it F at x. So if you can multiply F at x of this force, then it will give you the sense of direction where your force is going. So once you know your force, where is it going, then you know the direction of energy. How do I mean this? Because cos theta, if you think about it, this just gives us the direction of flow of energy. Because I said if our theta is less than 90 degrees, it means that we are going to get a positive value, and positive value means what? Means energy is transferred to the object, right? But now let's take a look at if we are having, if we just said, okay, if our force is going that way, it means that if our force is going same direction as our object, then it is positive work. If our force is going in the same direction as our object, then it is positive work. It is positive work. So this, again, like I said, you must have the knowledge of Newton's laws and the knowledge of forces. We all know that when we are picking our direction, we always pick the direction where our object is going. We always pick a direction where our object is going. So it means that based on this object, or checking on this object, it means that this force, if we calculate its F at x, it is going in the same direction as the object. So it means that already that force will be a positive force. So all the forces, so this is just a tip that I want to give you. So all the forces going same direction as the object, we say they are positive forces. So it means that all the forces going in the opposite direction, all the forces going in the opposite direction, they'll be negative forces, right? So all the forces going in the direction of the object, we call them positive forces. So having said that, it means that our new way that we can use to calculate this work done by this force, we can do like this. It means that our work is equals to F changing x, like that, right? So it means that first thing first, we can calculate our force in x. So how do you calculate our F at x? We say F at x is equals to F cos of theta. So it means that F, which is 50 cos of 60, and then we can get our 25 newtons. So the horizontal component of this force is 25 newtons, right? That is the horizontal component of that force. So now we can come and say the work done by this force, right, will be equals to 25 multiplied by the displacement, which is 10. So now we can get our 250 joules. And don't forget that this force here, we put it as a positive. Why? Because it is going in the same direction as your what? As your object. So we're going to have positive work done by this. So it means that our work becomes positive work. So it means that energy is transferred to the object, or the object gained energy, right? So this is about the positive work and how everything goes about the positive work. So now let's take a look at the negative work. Now let's take a look at this now, negative work. So how does the negative work, how do you find the negative work? So again, I explained about this theta thing. So if our object, maybe it is going that way. So our object is going to the right. So this is our displacement. If there's maybe frictional force, you know that it always opposes the motion, right? So if we take a look at the angle between the frictional force and this direction of the object, we can see that the angle between there, it is 180 degrees. So this angle that is 180 degrees, it is greater than 90 degrees. So whenever that we're having a theta that is greater than 90 degrees, what do we have? We always have a negative value, right? We always have a negative value. So if we include the negative on the formula that says that work is equals to force and then cos of theta, then it means that that theta will always give you a negative value because it is greater than 90. And when this happens, it means that you're going to have a negative work, the work that is negative. So if your work is negative, what does it mean? It means that energy is lost by the object. Energy is lost by the object, or energy is transferred out of the object, right? So this is what happens with negative work, right? But now, how do we calculate negative work? Again, I'll show you the two ways. This first way that you include theta, and the other way that you don't have to care about theta, you just have to know your directions. Know your directions. Because again, I've already explained that if the force that you are having is in the opposite direction as your what? As your object's direction, then it means that that force is a negative force, right? That force is a negative force because it is going in the opposite direction to the motion of the object. But if this force was going in the positive direction, or in the direction with the object, then you're going to have a positive work, right? But in this case, we're having a negative force. The negative force. So let's try to look at how this comes about. So let's take a look at this. This object is going to the left. This object is going to the left. And it moved a displacement of 10 meters. And we're having the force applied, that is 20 Newton, applied at a 60 Newton to the horizontal. If you take a look at this force is acting in the opposite direction to motion, right? So the way that they show us to calculate work done. So it means that work done by this force is equals to F and then cos of theta, right? So the problem that I have with this formula that they said you must use cos theta is this. At some point you end up being confused with this theta because at some point you place this theta, and this is not the theta that you are supposed to place. Why? Because this object is going to the left and this force is applied to the other side. It will mean that our angle between the force and the direction is this. This is the angle that we must be using. And what angle is that? That angle becomes 180 minus 60, which will give us 120 degrees, right? So that is the problem that I have with using this formula that includes cos theta. Because at some point you end up being confused with this theta, which theta to use, right? But according to this, it means that our force becomes what now? Our work becomes the force that is 20 multiplied by the displacement that is 10, and then cos of 120, right? And when you do that, we can get the value that is negative 10. Is that so? Is it negative 10? No, I mean negative 100. So this will be negative 100 joules. So if this is negative 100 joules now, what does this mean? It means that we got a negative value, and a negative value means energy was lost by the object, or the transfer of energy was transferred out of the object or from the object. That is the energy transfer that happened here, right? And now with the formula that I always advise students to use, it is this one. So I said I always advise you to use F work by force is equals to F changing X, like this, right? Without the what? Without the cos theta. And how are we going to apply it in this case? So in this case, first thing first, we have to calculate the what? The F at X of this force, which is the horizontal component of this force. So how do you find the horizontal component, the F at X of this force? So guys, this was done mostly in vectors, right? So if you are not familiar with the vectors, please revisit your vectors, right? So if we're trying to find the F at X of this force, it means that our F at X is equal to F cos of theta. And which theta are we going to put? We are just going to put this. But now we know that if this force that is here is at an angle, it means that it has a vertical component and also a horizontal component. And our horizontal component here, it will be going to the right. So let's calculate our horizontal component. So F at X is equals to F cos theta. Then it means that our 20 and then cos of 60. And we're going to get the force that is 10 newtons. That is going to the what? To the right. But our object is going to the left, right? So our force is going to the left. Our object is going to the left, sorry. So object going left, but force going right. So when our object is going to the left and our force is going to the right, it means that the way that I explained, I said, whenever your force is going in the opposite direction with the direction of the object, then you are going to place that force as a negative force. So it means that now to calculate the work done by this force, we'll just place it as work done by that will be equals to our F at X, which is 10, multiplied by the change in X, which is also 10. But I said this force, we must place it as a negative now. We must place it as a negative. Why are we placing it as a negative? Because it is going in the opposite direction as the direction of motion, right? This object is going to the left and this force is going to the right. So it means that we are going to place it as negative. So it means that now the work done by this force will be equal to negative 100 joules, which is the same as that. Can you see that? So this formula I only have a problem with how it can confuse when it comes to the forces that are going in the opposite direction. Because now you have to apply this 180 minus theta things. At some point you end up forgetting. But once you can just calculate your your horizontal component of forces. If you can calculate the horizontal component of a force at an angle, if you can be able to calculate the force, the horizontal force that is done by the force that is at an angle, then you can be able to calculate the work done by that force, keeping in mind your direction. So you must keep in mind your direction, because direction is always important. So it means that if your force horizontal component is going to the left and the object is going to the right, then it means that you are going to put that force as a negative force. Yes, so let's go to zero work. Now let's talk about zero work, right? So zero work, this is a simple stuff. So zero work is done whenever that your object is going left or right, and the force that is being in topic is the force that is acting perpendicular to the plane. So whenever we're having a force that is acting perpendicular to the plane, then we know that it is going to give us zero work. Why? Because if you just press cos 90 in your calculator, you get 0. So if cos 90 is equal to 0, it means that our work, since we know that work is equal to F and then cos of theta. So if this becomes 0, then it means that everything becomes 0. So it means that the force that is done, if the force acting on an object is perpendicular to the motion, if it is perpendicular to the direction of the object, then it means that no work is done, or zero work is done. So there's no energy transfer there. No energy transfer. So there's no energy transfer in this situation because this force is acting 90 degrees. So these are forces like normal force. And guys, quote me right. I said these are forces like normal force. Normal force always gives us zero work. It always gives us zero work. And then we have Fg. Fg, when we're acting on a parallel, when we're acting on a horizontal plane like this, Fg always gives us zero work as well because it is acting 90 degrees. It is perpendicular to the plane, right? But when now we're on the inclined plane, it means that Fg won't have zero work. So here, Fg will not give us zero work. But when we're on this situation, Fg always gives us zero work. And normal force gives us zero work. And also here, normal force is always zero work, right? So this is when we're having zero work. So there's no energy transfer and there's no energy loss there. That's when we are doing zero work. So having said that, guys, it means that let me just cut this video in half so that it won't be too much long. It will be tedious to watch. But guys, if you haven't subscribed to our YouTube channel, please subscribe. And you can also like, share with your other mates. And the next video that I'll do, I'll start on network done. And I'll also do the work energy theorem. Right? So see you on the next one, guys.